Welcome, everyone. This is the third talk of session 3 of this conference. We have with us Dr. Pabitra Barman from IISER Mohali, and he's currently a postdoc there. He will be speaking on dominating surface group representations in PSLNC and PU21. Over to you, Pabitra.
Yeah, okay. Thank you, Shomada, for the introduction and the invitation. This will be joint works with Subhojoy Gupta and Krishnendu Gangavathan. Okay, so I'll begin with some motivation and background. The translation length of an element phi in PSL2C is defined to be the infimum of dx phi x for all x in H3. Okay, so here H3 is the real hyperbolic 3 space and the distance is taken in H3. Okay, remember that H3 is the symmetric space of PSL2C. In fact, this PSL2C is the group of orientation preserving isometries of H3. Okay. Now let S be a connected oriented topological surface of negative Euler characteristic, and rho be a representation from pi1s to PSL2R, which is discrete and faithful. Okay. Note that such a representation rho determines a hyperbolic structure on S. Okay, on the topological surface S, that that hyperbolic structure is unique up to isometry. Okay. Now, let gamma be a closed geodesic on the hyperbolic surface S. Then the hyperbolic length of gamma is exactly equal to the translation length of rho gamma. Okay, so whenever I say a translation length, at the back of your mind, you can think this as the length of some closed curve, but definitely that happens in a good enough situation. Okay, so moving on. Let rho1 and rho2 be two representations from pi1s to PSL2C. We say rho2 dominates rho1 if there exists lambda less equals to 1 such that the translation length of rho1 gamma is less equals to lambda into the translation length of rho2 gamma. Okay, and that this happens for all gamma in pi1s. If this happens for all gamma in pi1s. Okay, we say that this domination is strict if lambda is strictly less than 1. Okay. Now, domination in surface group representation variety, it first appeared in the context of ADS 3 manifolds, anti-de-Sitter 3 manifolds. In 2015, Goreto, Kessel, Wolf, they first proved that for a closed surface SG and non-Fuchsian representation rho from pi1 SG to PSL2R, there exists a Fuchsian representation J that strictly dominates rho. Okay, here recall that a Fuchsian representation means discrete and faithful representations in PSL2R, right? This theorem has direct application in the construction of ADS 3 manifolds, and their proof involves the idea of a folded hyperbolic structure. Around the same time, Deru and Tolosa, they extended the result for surface group representations in PSL 2C. Okay, and their proof is analytic and it involves harmonic maps. Okay, let me here mention that a Fuchsian representation cannot strictly dominate another Fuchsian representation. Okay, and this is due to Thurston. Now, all these results were done for closed surfaces. What about punctured surfaces? Well, the following theorem by Gupta and Shu, it says that let SGK be a punctured surface of negative Euler characteristic. Okay. Now, for a non-Fuchsian representation rho from pi1 SGK to PSL2C, there exists a Fuchsian representation J from pi1 SGK to PSL2R that strictly dominates rho while preserving the lengths of the peripheral loops. Okay, so peripheral loops means that loops around the punctures. Okay, now their proof involves straightening of row equivalent pleated planes in H3. So as you can see the pictures, the left hand side, this is the row equivalent pleated plane in H3, and their proof was completely geometric. And now observe the last line of the theorem that says while preserving the lengths of the peripheral loops, right? So why do we want to preserve the lengths of the peripheral loops? As a matter of fact, if we are allowed to increase the length of the peripheral loops, then even a Fuchsian representation can be dominated by another Fuchsian representation. Okay, and one such example is Thurston's strip deformation, where we cut along a bi-infinite geodesic that is going out to some flaring end. Okay, and we graphed a hyperbolic strip in between. Okay, so the resulting hyperbolic surface we get that dominates the initial hyperbolic structure. Okay, so coming back to our original so now our concern is that whether this kind of dominating phenomena happen for higher rank representations or not. Okay, for example, for representations from pi1 s to psl in c with n greater than 2, right? So here the first question is that what should be a correct notion of length for these representations, right? Well, for a representation rho from pi1 s to psl in c, we define the row length of a curve gamma in pi1 s to be log mod lambda n by lambda 1. Okay, where these lambda n and lambda 1 are the largest and smallest eigenvalues of rho gamma in modulus respectively. Okay, here note that this is exactly the translation length of rho gamma if rho is discrete and faithful and n equals to 2. Okay, and this is also known as the Hilbert length of gamma. Okay, now also consider the symmetric space PSL in C mod PSU n with the standard Riemannian metric, and this is also the set of Hermitian positive definite n by n matrices of determinant 1. The translation length of an element A in PSLNC in the symmetric space Xn is given by square root of sum of log mod lambda I of A square. Okay, where these lambda I, these are the eigenvalues of A. Okay, now the analog of Fuchsian representation, the in higher rank representations, they are known as Hitchin representations. A representation rho from pi1 s to psl nr, it's called n Fuchsian if it can be written as a composition of a Fuchsian representation J, okay, and the unique irreducible representation from PSL to R to PSL nr. Okay, now for a closed surface, the connected component containing these n Fuchsian representations in PSL nr character variety, that is called a Hitchin component. Okay, and elements in this Hitchin component, they are known as Hitchin representations. Okay, note that these Hitchin representations are all discrete and faithful representations. Okay, and they are also positive representation in the sense of Fock and Goncharov. Well, what are positive representations? I'll come back to it in a few more slides. Okay, okay. Moving on and coming back to our original concern, that whether dominating phenomena happen for higher rank representations or not, the following theorem has an answer. Let FGK be a connected oriented topological surface of negative Euler characteristic and punctured surface. Okay, now for a generic representation rho from pi1 SGK to PSL NC, there exists a positive representation J from pi1 SGK to PSL NR that dominates rho in the Hilbert length spectrum as well as in the translation length spectrum. Okay. Moreover, the lengths of the peripheral curves, they remain unchanged. Okay. Now, and there is no good analog of a pleated plane in the symmetric space of PSL NC. So we cannot be geometric anymore. So we have to be algebraic, and we'll use something known as Fogg-Goncharov coordinates. Okay. So you can think these coordinates. I really don't have enough time to talk about these coordinates, but one can think these coordinates as the generalization of Thurston's shear bend coordinate. Okay, what do? They parameterize a generic class of representations from pi1 SDK to PSL NC. Okay. Again, now let me just explain what I mean by a positive representation. Well, the representations that have these Fogg-Conchoff coordinates, real and positive. If okay, so that means if all the Fogg-Conchoff coordinates of a representation are real and positive, we call it a positive representation. Okay. Now, let me give you some a brief idea of the proof. So, so given a generic representation, rho from pi1 SDK to PSL in C. How do we define the positive representation? We first compute the Fogg-Conchoff coordinates of this row. Then we replace each of the coordinates with their absolute values. Okay. Then we define the positive representation J to be the representation corresponding to these real and positive coordinates. Okay. Now, uh, uh, as an immediate consequence, we get that the J gamma, the matrix J gamma, it dominates mod of rho gamma entry wise. Okay, for all gamma in pi1 is GK, and this also implies that, and almost immediately we get that the largest eigenvalue increases in J gamma, and the smallest eigenvalue of rho gamma that decreases in J gamma. As a consequence, we get that this J gamma dominates rho gamma. Or the J gamma we construct from this dominates rho gamma for all gamma in pi1 SDK. Okay. Also, as a consequence, what we get is that uh, let lambda1, lambda2, lambda n be the eigenvalues of rho gamma in increasing order in their modulus, and let lambda1 dash up to lambda n dash be the eigenvalues of J gamma with the increasing order in their modulus. Then the product of k, the largest k eigenvalues and their modulus, that also increases here. That is also less equals to mod of lambda k dash up to lambda n dash. Okay, so that means the product of the k largest eigenvalue that also increases for all k in from 1 to n. Okay, so this proposition along with some other standard inequalities help us to prove the domination for the translation length of rho gamma in the symmetric space xn. Okay, now what happens for a peripheral loop? Well, for a peripheral loop gamma, rho gamma becomes a triangular matrix with the diagonal entries as product of these coordinates, okay, and their reciprocals. So when we replace the coordinates with their modulus, uh, the length, the translation length really does not change. Okay, so this means that it preserves the length of the peripheral loops also. Okay, so this is the first part. Any questions so far? I'll now move to the second part of the talk. Well, if not, let me move. So consider C21 with respect to the non-degenerate indefinite Hermitian form given by this quantity. Okay, so these can also be expressed as W star J Z. We have seen this just in Sagar's talk a few months ago. So this is the Hermitian form of signature 2, 1, meaning that it has this Hermitian matrix has 2 positive eigenvalues and 1 negative eigenvalues. Uh, the complex hyperbolic space HC2, this is the projectivization of the negative vectors with respect to these Hermitian form. Okay, so we take the negative vectors and we projectivize them to get the complex hyperbolic space HC2. Okay, let U21 be the group of matrices preserving this Hermitian form. Okay, now for a matrix A in U21, it turns out that A star JA is equal to A. Okay, so for a matrix in AT1, A has to satisfy this condition that A star JA equals to J, but J is this matrix. Okay, so the group of holomorphic isometries of this complex hyperbolic space, this is given by PU21. Okay, so basically we take the projectivization of PU21. Okay, nice. Fine. So the Bergman metric on HC2 is given by this expression. So where Z and W are the some representative of these points Z and W. And note here that we can actually choose any representative here, doesn't matter, that cancels out and give us the same quantity. The Barman translation length of an element A in SU21, okay, in SU21 is given by log sigma of A, where this is the largest eigenvalue, okay, spectral radius, okay. And so for an element A in PU21, how to define the Barman translation length? Well, we take the lift of that element A in SU21, and any two such lift differ by product with some unity of root of unity. Okay, so whenever we take the more spectral radius, it doesn't change, so it doesn't matter. So yeah, we take a lift in SU21 and we use this formula to get the translation Barman translation length of an element in PU21. Okay. Now the plane HC2 intersection R2 when they are non-empty, and its image under PU21, they are totally geodesic subsets known as Lagrangian planes. Okay, they are. This turns out to be the Klein-Beltrami model of hyperbolic plane of H2 that is embedded in HC2. Okay, they are the subgroup of PU21 that preserves these Lagrangian planes. We denote it by PU21. Okay, and let T be an ideal triangulation of SGK. So ideal triangulation means a triangulation on the surface SGK where all the punctures lie on the boundaries. Okay, on the punctures. Sorry, all the vertices of the triangle lie on the puncture of the surface. Okay, so no vertices lie actually on the surface. So this is called ideal triangulation. So now I'll define a quantity known as T-bent representation. So what is it? So suppose a representation rho, we have a representation rho from pi1 SGK to PU21. It's called T-bent if there exists a rho equivariant map known as framing phi from F infinity to the boundary of del H2. Okay, I'll come to these terms, what these terms are. Okay, such that for any ideal triangulation del in T tilde is the universal cover of T, with vertices A, B, and C in F infinity, the images phi A, phi B, and phi C form a real ideal triangle in HC2. Okay, let me explain what these terms are. Okay, so F infinity. So F infinity, it's called the Faraday set. It is the lift of the punctures of the surface in the universal cover, in the boundary of the universal cover. Okay, so this is called the Faraday set, F infinity. Now, and del HC2, what is this? This is the boundary of the complex hyperbolic plane. That means it's the projectivization of the null vectors. Okay. Now if we, so what they say is that, what the definition say is that you choose vertices, you choose any triangle from the lift of T, you take the vertices ABC, and if the framing if the image of the framing phi A, phi B, phi C of the three vertices, they form a real ideal triangle. So what is a real ideal triangle? Well, if all these three vertices lie on the boundary of a Lagrangian plane. Okay, because that we just said what Lagrangian planes are. They're also known as real Lagrangian planes. If the image of these three vertices, they lie on the boundary of a real Lagrangian plane, we'll call it a real ideal triangle. Okay. Okay. Fine. So now the next result says that let SGK be an oriented surface of negative Euler characteristic with at least one puncture. For a T-bent representation rho from pi1 SGK to PU21, there exists a discrete and faithful representation rho naught from pi1 SGK to PO21 that dominates rho in the Barman translation length. Okay. Moreover, if gamma is an element in pi1 SGK, which is a peripheral loop, means loop around the puncture, then the Barman translation length of rho gamma this remain unchanged. Okay. So we use the invariant associated with a pair of adjacent real ideal triangles. So if we have suppose let me probably draw the picture here quickly. So if we have adjacent pairs, so we take the leaves, and if we have such an adjacent pair of real ideal triangles, then we can define an invariant, uh, and then that invariant, we have used that invariant again. So this is again somehow similar to the Thurston's. This invariant is again, yeah, similar to that of Thurston, given by Thurston's shear bend coordinate, but not exactly that. I mean, we need different setup for this, and we have used these coordinates to prove our result. Well, here are some of the references, and thank you. Yeah.
Thank you, Pabitra. Any questions?
So hello, Pavitra.
Hi.
How are you seeing like the representation of the fundamental group of the surface inside PSL2C? Just I don't know. matlab.
Can you ask again? The question is not clear actually to me.
So I think in the first or second slide you said
Yeah.
you were looking at the I don't know. It is canonical that it is canonical representation of the fundamental group of the
You're talking. Are you
surface.
talking about these things?
Yeah, right. Yeah.
So,
Yeah.
yeah. What is the question? So,
So
how?
how do you construct it, or is it very easy, or you can give me some
What is
reference
the
to look at?
No. Yeah, it's fine. That's fine. I mean, yeah, it is. It's a thing that corresponding to each hyperbolic structure on a surface, we get such a representation. Okay. So, are you familiar with the holonomy and developing map and holonomy, all these things?
No, I'm not
Oh, okay,
familiar.
no problem. So, developing map and holonomy, this is a pair, sometimes written together. So, holonomy, so what is a developing map? Developing map is a map that is defined from, in our case, it is on H2, okay? So, this H2 might change differently in a different things. So, and H tilde is the universal cover, okay? And here, with this developing map comes a holonomy map, which is actually equivariant. Holonomy map is from pi1s to the group isometry PSL to R, and this satisfies some properties. Okay, this is a homeomorphism, and this is a transverse map. Sorry, what I mean is the equivariant map. Yeah, and this becomes a homeomorphism, and this holonomy in our case becomes the rho. Okay, so for a given hyperbolic structure, so suppose we have a hyperbolic structure on the topological surface S. So for that we get such a pair, developing map and holonomy map, and this holonomy map, it becomes this rho. Okay, this pi on S. Okay, this gives you one side, right? So from the
Okay.
hyperbolic structure, you get such a discrete and faithful representations, and it turns out to be discrete and faithful. Now, if you have such a representation, if you have a discrete and faithful representation, then what do? You just take H2 and quotient it by the image of pi1s. Okay. So now what you get is exactly S with some hyperbolic structure. So this gives you the one-on correspondence between the discrete and faithful representations from pi on S to PSL to R, and the hyperbolic structure. Well, actually, to be precise, if I want to be precise, they are marked hyperbolic structures on S. Okay, that means S gets a hyperbolic structure along with a marking at a homeomorphism that maps the topological surface to the to the hyperbolic surface. And yeah, that's it. I mean, I just showed the one-on correspondence. Did I answer your question?
Okay. Yeah. Thanks.
Yeah.
You will be like okay. I will talk to you maybe later on these things.
Okay. Sure.
Can I ask one question?
Yeah, sure.
Yeah, if you take PUN1, this question you solved for PU21, but what is
Okay.
difficulty for PUN1 thing actually?
Okay. Yeah. The first
Or
thing is
generally,
that yeah, right. The first thing is that we don't yet at least I don't know about the coordinates yet. So I have used some special coordinate here. Okay, so that I call this is somehow similar to the Thurston's shear bend coordinate, and this is given by Will, actually Pierre Will, the Z coordinate that involves 4 points. Okay, the adjacent ideal tetrahedron. Okay, but for a general case, for a representation into pu n1, at least I don't yet know if there exists such a coordinate that parameterizes these kind of representations. Okay, that is the first difficulty. I mean, one can try to think this geometrically, but I'm not sure. I mean, that's the thing.
Okay, okay.
I
And
guess
for
the similar kind of
PSP21, actually for PSP21 that makes sense actually. These questions, yeah.
right, exactly. You are right. You are absolutely correct. So if we have this kind of bending, so for example, let me just tell you that in the T-bend representations, right? If you see the definition, we have seen that these we have defined it like phi A, phi B, phi C. They form a real ideal triangle. Okay. So
Hmm.
what happens? So you know that complex planes are also totally geodesic subsets similar to the Lagrangian ones, right? But they have these holonomics. They have this yeah. So the problem here is that we can't even bend along a complex plane also. So this is one. This is a case for real alien triangles only. We can't even bend along some complex planes also. So
Okay.
it's not just yeah. The problem is here. So because the complex planes, actually, we can see it by computation also that complex planes have the holomorphic structure and all this. Yeah, but yeah, you are right. So these questions
Yeah,
make
yeah.
sense
Thanks.
in other Lie groups also. Yeah, right. Yeah,
Yeah, yeah. Thank
one
you.
should. Any more questions?
Any other questions? If not, let us thank the speaker. Thank you, Pavitra.